yeah, just improvements to products that are being produced.
I believe Mark is first on the agenda. Mark, are you planning to share some slides?
You know, I don't see him on
either.
So I'm going to email him right now.
Nathan, you're next. Would you like to go ahead?
Sure, I can present. We'll try to. I'm a bit new at Zoom and sharing screen. Usually use NASA Teams, or not NASA, Microsoft Teams.
There's a green share screen button that should be at the bottom.
Okay. All right, it is sharing my entire screen. Can you see the presentation?
Yes.
Okay.
Looks good.
Okay. So wanted to talk about some low latency products from ISAT2. Just to jump right in. Right now, ISAT2 is producing a number of data products included in those. This is our full chart of data products, and some of these are still in the planning stages. But it starts at the lowest level data and then works up to derived products. So the one that the sea ice community would be using would be ATL 07 and 10, the sea ice elevation and freeboard, and then gridded products, things like gridded sea ice freeboard, and then in the future, gridded sea surface height. So right now, the standard products are produced with something like a 45-day or longer latency. And mostly that's due to getting quality orbit solutions to do the products. We do generate rapid products, and so the community has really been calling for these rapid products for things like sea ice forecasting. And so this is just done for the internal health and evaluation, but we've been working with the NASA Satellite Needs Working Group to assess the impact of generating rapid products, actual products that could be used by people with something like a 3 to 5 day latency. And so, again, some of the motivation, I don't need to preach to the choir here. This is a figure from one of Rick Allard's papers showing Cryosat2 assimilation into a model and how that helps improve sea ice forecasts. So what we wanted to do was assess, okay, how good are the rapid freeboard and thickness data that ISAT2 could produce, and are there errors inherent in the rapid processing? And again, some other motivation. Here is a slide shown at the ISAT2 science team meeting last week, a recent paper that Sinead Farrell was involved in, and she passed this along. And again, highlighting one of the statements here is, again, ice services across the world could benefit from a rapid release ISAT2 product. This was looking at ridging, degree of ridging from ISAT2. And so again, releasing rapid products could enable things like looking at ridging or sea ice freeboard and thickness at a really quick scale. So jumping in, how good are the rapid products? So we did an analysis of these. This is from October 2020, and this is just a 25-kilometer scale grid of the final and rapid products. So here's the grids, the difference, and then histograms of those. And so this looks really, really good. We're seeing very little difference between the final freeboards and the rapids. Really no mean difference. 2 centimeter standard deviation of difference. And if you look at the map, just a few grid cells, which are anomalous here. The bad, though, is the actual heights themselves. We did look at granule to granule comparisons. This is a granule of one of the final data products here in red, and then the rapid in blue. And it shows something like a 3-meter height bias. It doesn't look like it's due to the geophysical corrections that we use in a rapid scale, but rather in the orbit solutions. And so these are meter scale height errors. So if you do a scatter plot here, it looks pretty bad. I don't think this is particularly meaningful. Again, this is a really long orbit, so you're going to see pretty big jumps in the sea surface height over thousands of kilometers, and that's what leads to this kind of scale. So looking at this, actually just deriving freeboard. So freeboard's a relative height measurement. You find a nearby lead, you take the sea surface height from that, you subtract it, and then you get freeboard. And so doing this at that scale really removes those orbital variations, which are pretty large scale. And so ultimately what we see is this, doing this granule to granule comparison at the freeboard level, is that they're almost equivalent, almost no mean difference. And then again, what we see is on the order of a 1 to 2 centimeter standard deviation for the rapid products. So what we think we can do is, we think these look really good. So they should be near the same quality as the final products. And so the final products right now from previous papers led by Ron Kwok showed our uncertainty in freeboard is somewhere on the order of 2 to 4 centimeters. And then we're introducing an additional 1 to 2 centimeters in the rapid products. So if you add up the errors, there's not a large difference from this 2 to 4 centimeter error that we currently have. So we think we can do this with a 3 to 5 day latency. We're hammering out the final details on doing this, but we're aiming for September or earlier release of these products. And they'll all be hosted at NSIDC. So right now the ISET2 products are at NSIDC, and they'll be put in basically a similar flavor. The rapids will be removed as finals become available. But really, they're meant to just be the same. The same code is used to get these products. And then a new sea ice thickness product was also put up. I believe Walt will talk a bit about that. To get thickness will require using climatology snow, because otherwise we don't have observations of snow for the thickness. But by and large, look for these products in the coming months. Any questions, or if we're going to save those for later?
Maybe if anyone has any quick questions. No. In the meantime, Mark, are you ready to present next?
And Mark, the mute button is in the bottom left of the screen. Let's see.
Am I unmuted?
Yes.
Yes.
Oh, great. I did the Alt A. Yeah, sorry. I was under the impression this was going to be at 3 o'clock Eastern. So I just got a message from Walt to get in. So, okay. So I will try to, I'm not familiar with Zoom, believe it or not. So I'm going to try to share my screen. Somebody want to, let's see, how do I do that?
Yep, there's a green button in the middle of the bottom of the screen, share screen. And if you click that, it should come up with options.
Oh, I see it now. Okay, somehow I got out of that screen, so now I see it. Okay, and then, all right, first I need to open my presentation. Please bear with me. Okay. I'm just opening my presentation now. Okay. Slideshow.
happy to share it from my screen if that's helpful.
Okay, I think I'm almost there. I just need to get this Zoom window back up. And now this, yeah, I'm sorry. The Zoom window is not, the main Zoom window is not coming back up now.
It's okay. I have it right here.
Okay.
Yep.
So, all right, I can't even, I wish I could enlarge it because I can't, I can barely see it. All right, sorry for this. Can I at least enlarge that? So, well, I'll go through mine and while you click yours. How's that? Doing what I can, sorry. Okay, so so everyone can hear me, and I'm not sure if you can see me, but my apologies for my Zoom ignorance. So I'm Mark Chudy. I'm at the University of Colorado Boulder at CCAR, which is a group within the Department of Aerospace Engineering. And I'm going to be talking about the NSIDC, sea ice motion, and age products. So we can go to the next slide. So first I'll start with a couple details on the sea ice motion product. Some of you are probably familiar with this, but others may not be. So first of all, we have two products for motion and age. One product is what we call like the production product, and that is our final product. Both of these are, and the other one is called the Quick Look product. So these are both archived at the National Snow and Ice Data Center. The production product, you can see the citation there for it. Myself and Walt also on the call. Also Scott Stewart, who is kind of the workhorse for the product in terms of doing the coding and the data processing and image creation. And then you can also see two other names there, Chuck Fowler and Jim Meslanik. They are the original creators of the ice motion and age products. And after they retired, I took them over and have continued to be the PI on them since they retired. So we currently have version 4 that is archived at NSIDC, and you see the URL there to access them. The motion products run from, as you can see, it's 1978 to the end of last year, and they are weekly motion products, and they are updated periodically. And the motion products cover the Arctic and Antarctic. The Quick Look products are created more often. We post them about once a month. And so they cover from the end of the production products. So currently from the 1st of January of this year. And at the moment they are through the 30th of April. And they are also weekly products and updated monthly. And the main difference between the Quick Look and the production is the Quick Look product uses a more uncalibrated passive microwave brightness temperature, which becomes available first. So we do the initial first processing while those passive microwave brightness temperatures are being processed to be calibrated. And so that uncalibrated one is fed into the Quick Look product. And so that's obviously so we can get the product out quicker to users for more recent data. Then okay, so we can go to the next slide. So the sea ice age product is broken down the same kind of way. We have a production product and a Quick Look product. And they are also weekly products and updated in the same fashion. The one difference to note is that the sea ice age product is only available in the Arctic. And also note that for both of these products, when you go to the website, you can not only download the data, but you can download the browse imagery that I'm showing examples of here. Okay, we can go to the next one. So this chart summarizes how the motion and age products are actually created. On the left, for more details, you can reference a paper that Walt and I and Scott published not too long ago that summarizes in more details. But you can basically see from the graphic that we import the passive microwave brightness temperatures, buoy from, oh geez, I'm forgetting the name of the buoy program. Sorry, Ignatius, from Ignatius Riggers buoys from the University of Washington, and NCEP winds. So we import those, create vectors from them, and then through an optimal interpolation process, we map the merged motion vector onto a 25-kilometer ease grid. That optimal interpolation is based on weighting the individual sources, so the brightness temperatures, the buoys, and the winds, according to a weighting system. So since buoys are really pretty much the truth of how the motion is doing, then we rate that the highest at 0.95. And then passive microwave brightness temperatures is weighted at 0.8 and wind at 0.45. And we also weight according to the distance of each source from the point that we're looking at for motion. And that distance falls off exponentially. And again, the more details of that is available in the paper. Also I note at the bottom that in the Antarctic, we don't have buoys that we import. There are not many down there, but any ones that are, we aren't currently using. So no buoys are imported for the Antarctic. And again, there is no age product in the Antarctic, although that's something we're considering it to do at some point. Okay, go to the next slide. All right, so I've decided that I need to come up with a new moniker for something, I don't know, for the effect of ice getting younger, because it's as I've presented this and these products have been discussed over the years. Sometimes there's kind of a quote that gets attributed to the ice age saying that the ice is getting younger. And so I decided I'm going to call that the Benjamin Button effect. But in actuality, of course, ice is not getting younger since things can't get younger, but we haven't discovered a fountain of youth. But as you might imagine, the older ice is being replaced by younger ice. So on average, ice is younger in recent times than it was in the past. So you can see this comparison, which was one we created for the Arctic report card, and we do each year, that shows the ice age on the top, the two browse images, one from March of 1985. And if you look real close, you can see the red is the oldest ice. So you can see that back in 1985, the ice pack had a large amount of older ice. And now in recent times, this is from March of 2020, you can see that the oldest ice is mainly just along the coast of the Canadian archipelago and Greenland. And then the image on the bottom just summarizes that statistically. And you can see again how in recent times, the first year ice is dominating the ice pack, whereas it was a different scenario with older ice back in the mid 80s. Okay, go to next slide. All right, so one of the applications we're started doing and will continue to do on a new project is Lagrangian tracking. So we're taking the sea ice motion product and looking at individual parcels or pixels really of the 25-kilometer ice motion product, and tracking each one of these as they move about in the Arctic. And we can track this over a year period or longer, as long as these parcels are still continue to exist. And at some point, you know, the parcels will either pile up at the coast, like we just showed, or like I just showed off the Canadian archipelago in North Greenland, or will melt out either in the Arctic or being exported out of Fram Strait and a couple other export regions. So in this case, we're looking at Lagrangian tracks over 1 year, and this is just a subset of the ones that we have available. There's over 1,000 we can look at any one time. And so you can see that the ones I chose here, you can see how they're moving, with the dots being the first point on the track. And then you can see that along with just the motion of the track, we are also tracking individual sea ice properties, such as, in this case, we're looking at ice surface temperature, albedo, ice concentration, and ice thickness. So we track these parcels and their properties. So this is, in a sense, like looking at virtual buoys, if you will, and tracking their individual properties, which really opens up a nice area of study to see how the motion of these ice parcels is affected by what they move through, if you will, what surface temperatures they move through, and how that's affected concentration and ice thickness. And of course, another big impact on the parcels is the underlying ocean. But we haven't. That's a tougher one to do. But one thing we could do in the future is also look at like sea surface temperature for the closest areas in the marginal ice zone, and for, you know, leads opening up, large leads opening up, and that kind of thing. Okay, so we can go to the next one. So, okay, so that's pretty much it for this presentation. I just wanted to acknowledge the project participants. We are just starting a 3-year study that is going to be making some more improvements to the ice motion age product by using enhanced passive microwave brightness temperatures, and we'll also be performing more Lagrangian tracking during this supported project. So the participants in this project are Walt Meyer and Mary Jo Brodzik and Scott Stewart from NSIDC, as well as myself, and we are getting support from the NASA Cryosphere program. So thank you.
Thanks a lot, Mark. We really appreciate that presentation.
Sure.
So do we have any questions for Mark at the moment, or do you think it's better if we wait for the discussion for those questions?
There's a question in the chat for Mark. Mark, I don't know if you can read that, from Dave Douglas. And maybe I can read it. He asks, have the daily ice motion products been dropped from version 4 distribution? One of your early slides just mentioned a weekly product.
Yes, the daily motions have been dropped from distribution. The reason we are not going forward with the daily ice motion vectors is we see in the daily motions a lot of scatter, a lot of just kind of, I don't know what the best word is to describe it, but kind of disjointed ice motions. And some of that is due to the way of just gridding the ice motion parcels. So we can get parcels that kind of jump around between grids. And we were finding that the daily motions were just kind of noisy and kind of scattered because of that. And that in order to reduce that impact and really provide a more meaningful ice motion, that we're just going to do the weekly ice motions.
Mark, I just want to jump in just to correct. That's for the near real time, the quick look, but we still have the daily for the historical archive, and I think we're planning to keep that going, even though those are noisier. And the weekly are better, but if you need daily, they are available. It's just they're not updated with the quick look, so they'll be updated.
Okay.
Like once a year or so. Yeah.
Okay. Thanks, Walt.
Great, thank you. There are several really nice questions in the chat from Yang Fei, Robert, and Mitch. But for the sake of time and staying on track, Mark, feel free to address those in the chat, or we can circle back to them in the discussion. But for now, how about we jump on to the next topic, and Walt Meyer's going to present the other sea ice products that are now on the NASA NSIDC. Walt, are you ready?
Yeah, thanks. Can you hear me?
Yep.
All right, let me share my screen. Where am I? Okay. All right, everyone see that?
Yep, great.
Okay. So yeah, I'm going to follow on. It actually builds on some stuff that both Mark and Nathan already talked about and referred to. So I'm just going to flesh that out in a little bit more than that. And the first is the ISAT2. Nathan did mention the sea ice thickness. That product is now out at NSIDC. As Nathan mentioned, it's not a standard product for ISAT2. When ISAT2, the products were being developed and designed and the requirements were being set, there was some concern about whether a sea ice thickness product could be a viable sea ice thickness product could be created because of the uncertainties with the snow cover. So it was not included as a standard product. But there's the recognition that there's strong interest from the research community. So it was supported to have a research project to see if you could derive useful thickness estimates. And indeed, that has bin shown to be possible using the freeboard ATL-10 product with NASA, this Eulerian snow on sea ice model, NESOSEM, for the snow loading. That was developed by Alec Petty at NASA Goddard, who also was leading the thickness. So the snow is added to the freeboard, and the different density assumptions are made to produce a monthly, at least during the winter time. These are October through April period at the moment, monthly fields. And this has been updated now through April of 2020. I think we'll probably be getting a new update at NSIDC pretty soon. I'm not sure exactly what the timeline, but these will be regularly updated. And then this is just another example. This is from Alec's paper and others from 2018, just showing kind of the freeboard on the left and then the snow depth, and then combining those together to get the snow thickness. So just showing another example there. The next one I wanted to mention is this measures CETB, calibrated enhanced resolution brightness temperature from passive microwave. This product's been around for a bit, but there are some new developments starting with this. It was originally supported by the NASA Measures program, a 5-year program to develop and get the initial data set out. This was led by David Long at Brigham Young University and Mary Jo Brodzik at NSIDC. And the idea is that it uses overlapping footprints and the antenna pattern to synthesize a higher spatial resolution. It's using the SIR algorithm, which I think is stands for like synthetic image reconstruction, if I remember correctly. And so that product was originally developed back in 2016, I think released in 2016 or 2017. And then that measures project ended. So that was the end of that production and development. But what we've done through the NASA Snow and Ice Distributed Active Archive Center, or DAC, which is at NSIDC, we have taken over that production of that product, and that is now being regularly updated roughly once a year. But we're actually working now to implement near real time updates. So there'll be daily updates of this product. And that product it contains SIMR, SSMI, SSMIS, and AMSR-E currently. But as Mark alluded to, we do have some funding both from NASA and from NOAA to add AMSR-2, which is the most recent, the JAXA AMSR-2 sensor, to that time series. So just showing you an example. So there is the standard 25 kilometer kind of drop in the bucket gridded resolution. And that's kind of what's been used historically. That's the standard product. But what they've done with this SIR reconstruction, they've created 3.125 or 6.25 kilometer resolution, gridded resolution products on the EASE-2 grid. And these are twice daily composites, and they're composited by local time of day, a morning period and an afternoon period. So that's a little bit different than typical composites, where they're either just a daily average or averages of ascending and descending passes. And so it gets closer to a more simultaneous, more synchronous gridding. And then it's currently updated through 2020. Like I said, the near real time version's in development. And this is just an example, the image on the right, of what you can get with this SIR algorithm. On the upper left is the standard gridded drop in the bucket. You can see the real pixelated values of brightness, temperature here, where you can see the low resolution quite clearly. And then on the right is 3.125 kilometers, and you can see how much sharper it is and how much more detail you see in it. And then the comparison with MODIS True Color Composite in the bottom right, and you can see the features match up quite well with the MODIS, which is 1 kilometer resolution. So the enhanced resolution really can provide potentially much better detail. And we've done some initial studies of these for sea ice, looking at this deriving sea ice concentration. And this is a paper that I published with Scott Stewart last year. And what we found was the 3.125 and the 6.25 kilometer, that comes out of the signal processing that they do, and that it kind of comes out of that SIR algorithm, but it's not necessarily the effective resolution. You get some smearing and some oversampling, essentially, based from what the true resolution is. So what we looked at was kind of the practical, what could you practically get out of it for sea ice? And what we've found is that you can easily get about twice the resolution, double the resolution of the standard product. So for a 25 kilometer sea ice concentration, which is what we standard distributed, we can actually get down to 12.5 kilometers, maybe a little bit higher. Mary Jo Brodzik is still, and David Long are looking at this further. And I think they have a paper that will have some more definitive answers to this. But what we looked at, what we found was about double, was quite good. And this is just an example, this image. So the standard 25 kilometer drop in the bucket is on the left. And then the enhanced at 12.5 kilometer is on the right. And the black outline is from a National Ice Center sea ice extent, the IMS, or what we call MAISY at NSIDC, and that's the ice edge. And right off the coast of kind of southwest Alaska. If you can see my cursor here, there's this little outline, and that's an open polynya, open water area off the coastline that the standard product doesn't resolve. It's too, the resolution is just too low. But at 12.5 kilometers, we see this open water, this white area, quite clearly that is picked up. So it really shows some substantial enhanced performance over that. So we see some initial potential for this, and the hope is that we kind of develop this further and start developing a time series out of this. And then the final product is actually a NOAA product. We have the NOAA and NSAIC group led by Florence Frederer. And so this is building off of the NASA Goddard products that we've carried for many, many years, and basically taking those products as the basis, but enhancing them to a climate data record standard, where the processing is fully automated, where we have provenance. It's a self-describing file format, NetCDF. And so we've upgraded these products. And this product originally came out back in 2013. It's been updated a couple times. Version 3 here. This is just an example field here of sea ice concentration. And what we're working on now, it's been delayed a little bit due to kind of last minute issues and some further snags that we've run into, but it should be out soon, a new version 4. And this is going to be I think a pretty significant update and upgrade to the product. One of the main things that we've done is we've added simmer to the record. Simmer was not originally processed with as a CDR variable because of some issues dealing with simmer, the data quality, and having the processing in-house set up for that. So the Goddard products went back to 1978, but the CDR product only went back to 1987. But with this new version, it will go back to 1978. And we do have a near real time version as well that's updated daily, and that will also be updated to version 4. And the other thing that we've done, and one of the other things that we've done is we've created complete daily fields through nearly all of the record. So we've added spatial and temporal interpolation, spatial for small areas like missing pixels within the grid, and then temporal interpolation for larger missing areas, basically interpolating from surrounding days. And with that, what we've done is added and filled in the missing simmer days. Simmer only collected data every other day. So from 1978 to 1987, sea ice concentration fields directly from the brightness temperatures are only available every other day. And that's the standard for the NASA Goddard products that we distribute, the Bootstrap and the NASA team algorithm. But what we've done with the CDRs, we've actually interpolated through those missing days and created fields every day. So that's very useful if you want to look at daily changes, if you're integrating or assimilating with models where you want to run the model with daily outputs. We now have the daily fields. And of course, these are interpolated, so you want to be aware of that you're not looking at real data, but interpolated data. And we do have flags for both the spatial and temporal interpolation. And this is just an example of one of the flag fields. The December 26, 1984 is Boxing Day of 1984. Excuse me, is a day where there wasn't actually data available. And so this is an interpolated field. These numbers, I won't go into the details of those, but basically the pink means that it's been interpolated. So the full field has been interpolated either plus or minus 1 or 2 or 3 days from surrounding days. And then the other, we've added a daily valid ice mask instead of monthly, and then fully refactored the software and updated the metadata. So that should be coming out within the next month, I would say, if not in the first half of that next month. And I'll just finish with one final thing. I want to just kind of push as a representative of the data center and the DAC scientists at NSAIC to please properly cite data in papers. And that means providing the full data citation, including the DOI in your references. Do not use just a generic reference like NSIDC sea ice data. We have many sea ice data, even sea ice concentration fields, so that's not a suitable reference. And also a common practice has been to reference the data in the acknowledgement section. And that is, it's nice to see that acknowledgement, but that's, again, not the proper method of citation. So please do that. In NSIDC, all our data sets have a citing these data tab with the full citation there in the recommended citation. So, and one final thing I'll just want to mention, we do have a Cryosphere seminar for those that are interested. Ellen Buckley is going to be presenting on remote sensing and observation of melt ponds on summer sea ice. And it's on Zoom, and we have a series, a link. I'll post these in the chat here after I finish up for folks to see. And if you don't catch it, feel free to email me and I can pass along the link. It's at 11 a.m. Mountain Time, 1 p.m. Eastern. So I will finish that. And if there's any questions, hopefully there's a little bit of time to do that. Oops, I should probably have put that share up just for a little bit longer.
Great, thank you so much, Walt. It was really nice to see all of those enhancements and advances being made with products. That was a really nice rundown. Does anyone have questions for Walt? Now's your time. And while you're thinking of your questions, I'm going to suggest that we try to multitask here because we're going to send a poll to you right now. And Meredith or Jana, I don't know if you want to give a quick blurb on what this poll entails. Oh, Janet, I think you're on mute. Oh, we can't hear you, unfortunately.
Okay, I can step in and just quickly say I put in the chat a link to a Google form, and I will start the poll when appropriate. It's a brief poll just to gauge where the sea ice team might fit into the next Arctic research plan. And so that poll kind of helps us think through some of those connections.
Great, thanks, Meredith. I do want to circle back. I think Yang Fei had a question for Mark regarding uncertainties. And Mark, you said that you expand on uncertainties in your ice motion product in one of your references, but I just wanted to ensure that Yang Fei's question was addressed. Is Yang Fei still here?
Oh, yes. Thanks. Can I ask about the exact reference here in terms of the uncertainty of the ice age products?
Yeah, I'm not sure. I might be on mute.
Oh, we can hear you.
Oh, you can't hear? Okay. Yeah, I'm so bad at Zoom that I stayed off mute, I guess. Yeah, I put the reference in the slides for the paper. So I guess you could share that again, or however you want to do that. Or I could just put it in chat if that's easier.
Yeah, that'd be great. Thanks.
Yeah, sure.
Awesome. And Mitch, I think you had a question about comparing the drifts with buoys, but Sean, if you're still on, did you want to emphasize on your response to that?
Sure, yeah. So we're looking, we got a bunch of these trajectories from Mark and Scott, and we're mapping some other atmospheric variables to them for our analysis. But yeah, we're compared the tracks to ice mass balance buoys that we've collected, and the tracks look pretty similar. Obviously there is some drift, and if you know the starting point isn't quite lined up, then there's some variation, but overall they look quite close.
Great, thanks. And I think that relates also to your question, Robert, about the estimate errors and how those propagate into the Lagrangian product. Is that right? Okay, great. And then we have more questions. Jang Pei, am I saying your name right? Do you want to ask those questions regarding?
Yeah, I go with pain. So I have two questions for Mark on the ice motion. One is how good are inset winds in Arctic region, and normally, the model tend to be as good as the dynamics as well as the data that help setting initial and boundary condition. I would think in Arctic, both are probably not very optimal. So I'm just wondering whether they got a chance to see or estimate how good are those inset winds.
Yeah, that's a good question. And I don't believe in our paper we did a real analysis of the wind error, because it's difficult to estimate the wind error versus our product because we ingest the winds into our product. But that one of the acknowledgements really of using winds from the NCEP fields that they are probably the least reliable of our three sources, being buoys, passive microwave, brightness, temperatures, and winds. We weight winds the lowest when we're doing our optimal interpolation. So that kind of reflects of how we prioritize the sources, with winds being the lowest priority of our sources we ingest.
Thanks. That kind of related to my second question is the buoys. And in the polar region, they're very scattered. So I'm wondering whether you estimated how much variance actually captured by the buoys.
Well, again, what we do is we weight buoys the highest when our vectors are the closest to the buoy locations, and then we drop off by distance as we get further away from the buoys. So probably the best way for us to estimate error versus buoys is what I forget who the other person was just speaking. Sorry, that is writing a paper on
Sean,
that.
I think. Sean.
Yeah. Okay, thanks. Yeah, John. Okay. Sean. Okay. Yeah. So that's is the best way to do like a kind of an independent assessment of how our product is doing versus the buoy motions.
Yeah, I think there's another way to do it is say just look at your product variance, and then also look at the buoys variance, and then see how much that can be explained by buoys variance. That kind of give you how much contribution from buoys in terms of the variance.
Yeah, that's true.
Thank you both. Since we only have a minute left, I'm gonna invite people to do a very speedy community update, and feel free to follow up with one another after this meeting. But does anyone want to share something publicly or in the chat about anything coming up related to sea ice collaboration team activities?
Hi, this is Betsy. I just wanted to note and bring everybody's attention to the fact that we will be sending a call out for the 2021 Sea Ice Outlook June report, and that'll be coming out either tomorrow or Wednesday. There are several changes from prior submission processes, and including a call for optional sea ice extent anomalies this year. So pay more attention to the details in the call than you might otherwise, and please share the call widely with anyone else who might be interested in participating in Sea Ice Outlook this year. Thank you.
Fantastic. Thank you, Betsy. Are there any other quick updates? If not, I see that we're a minute past. Thank you all very much for attending today, and I really appreciate the speakers and their presentations. Those were fantastic. So if anyone has anything else, that concludes our meeting. Thank you all very much for your time today.
All right. Thanks, Melinda. Thanks all.
Thank you.
Thanks, everyone.
Yo.